Okay, so in this section, we're going to be taking a look specifically at our electrons, and we're going to use them to explain how or explain some of the phenomena we observe on a regular basis. So we're going to first of all take a look at something known as the atomic spectra. And spectra here is just a plural word, the singular being spectrum. Okay, and we see manifestations of atomic spectra, for example, whenever you see a neon light, right? So things like down here, the ability for those things to give off that light is what's known as the spectra, or the spectrum of those particular elements that are in those tubes, those gas tubes. When the light comes off of an atom when it's heated, it comes off as a stream of particles known as photons. All right, you can think of photon as being like a little packet or a bundle of energy, which is known as a quantum of energy. It is a form of electromagnetic radiation, so it does travel at the speed of light as an energy wave, and it does have characteristics of a wave, which we've seen before, but also characteristics of a particle. Now, one thing to keep in mind is that the energy of a photon of light or any other electromagnetic radiation is directly proportional to its frequency. And we actually saw that in the diagram from the previous section, right? And we alluded to it when we explained frequency and wavelength. We can also say now this relationship between the energy and the frequency, we can say as the frequency of EM radiation increases, the energy increases as well. Okay, and that's what directly proportional means. We can also say as the frequency decreases, okay, the energy decreases as well. All right, we use photons, on a regular basis. We use them, if you have to treat a tumor, for instance, we use high energy photons to do that. Photons are used in lasers to read your compact discs, your CDs and your DVDs, for instance. So they're all over the place, and we use them a lot. So we take advantage of the atomic spectra of elements to try to identify them, and you'll actually be doing this in lab, or you may have already done it in lab, but I'll give you just an example of where this is really, really important. If you have a sample, let's just choose an element like strontium, Sr, and we heat it up. As we heat it up, that atom, the atoms in that sample, they become what is known as excited, and they give off light. And if we pass that light through a prism, it actually breaks that light down into its component colors that we can then see as a spectrum for strontium, Sr. We can do the same thing with all the other elements. We can do barium, for instance. If we heat up some barium, we'll see some green light come off of it. If we pass that green light through a prism, we'll see that green light gets broken down into its component colors, which we see over here. All right, so these individual colors that we see, you can think of these as being fingerprints for each of those elements. So the one on top there would be the fingerprint for strontium, and the one underneath would be the fingerprint for barium. And just like your fingerprints, right, no two elements are going to have the same fingerprint, so we can actually use them to identify the elements. And that's what astronomers and scientists use to identify what elements are present in stars that are billions of miles away from us, right? They can take a look at the light coming off. We can use very sophisticated detectors to determine what elements are actually present. So these they actually do look like lines, spectra that you see. That's the light that's coming off of those elements that have been heated. So what's the basis for that observation? Well, we can go back to the model of the atom that we saw previously. Okay, so this is based on the Bohr model of the atom, which says that the electrons reside in these orbits or these energy levels surrounding the nucleus. Alright, so if this were my nucleus over here, I can have an electron in one energy level, or a second energy level, or a third energy level. Okay, so if I have an electron over here, and I give some energy to this atom, it may be in the form of light or heat. Okay, what happens is this electron can become excited. So we can excite the electron. And what happens is that electron jumps to a higher energy level. So it can jump to maybe all the way over here, further away from the nucleus. What happens over the course of time is that electron can then relax back to a lower energy level, so it can fall back maybe all the way back down here. And when it does so, okay, it releases now energy in the form of light. For example, it can be other forms of energy, but of interest to us is the light energy that it gives off. Right? So, for example, it can give off maybe some green light. And that's the basis for, things like fireworks, for example, right? All the different colors of fireworks that you see has to do with electrons falling back, relaxing back down to lower energy levels after they've been excited to higher energy levels. All right, so these electron energy levels are where the electrons are going to reside, and we designate these energy levels with what is known as a principal quantum number, which is designated n. All right, so these energy levels start with n equals 1, which has the lowest energy. So that's our lowest energy level, which means then that it's closest to the nucleus. And as the n value increases, okay, the energy increases, but also the distance from the nucleus increases as well. Okay, so there are a couple relationships here that we can see. As n goes up, the energy goes up, and the distance from the nucleus goes up as well. So the lowest energy level you can have is n equals 1, and then we can go up in energy. N equals 2 has a higher energy than n equals 1. N equals 3 has a higher energy than n equals 2. N equals 4 has a higher energy than n equals 3, and so on and so forth. All right, one example or a good analogy to this is if you use a bookcase to represent the shelves of the bookcase represent the energy levels. The higher up you go in the bookcase, the higher the energy level, the higher the n value, and the electrons can only reside on those shelves. There's no in between place where they can be. All right, and if that's the case, or that is the case, so we say that those energy levels are actually quantized, right? And what that means is that the energy, again, comes in packets. There is no in between. Okay, so there's one packet of energy that corresponds to this level. There's another packet that corresponds to that level. If you add another packet, it corresponds to this level, n equals 3. There's nothing in between here. There's no n equals 1.5, for instance. All right, so you're either in n equals 1, n equals 2, n equals 3, etc. There's nothing in between. So we say that's the quantization of energy of the electrons. So the electrons reside in these energy levels as you go further and further away from the nucleus. So when electrons change their energy levels from a lower to a higher energy level, they have to absorb energy in order to do that. All right, so if we provide some energy to an electron, and this is an electron right here, let me circle it. This is an electron. We're going to give it some energy, okay, maybe heat or something. Then this electron here absorbs that energy and it jumps to a higher energy level, so maybe over here. So it jumps to a higher energy level as it absorbs some energy. Then eventually it can relax back down. So what's happening here is it relaxes to a lower energy level, and as a result it gives off energy in the form of light. Okay, and in this case it is red light that it's giving off, which has a certain amount of energy associated with it. Well, if we give this electron maybe a bunch more energy, it can jump to a much higher energy level, maybe all the way up here. And now when it relaxes back down, it's going to give off way more energy than it did than the one above, right? So it gives off green light then, right? And this green light has more energy than the red light above, right? And you can tell because the difference here in energy levels is much greater compared to over here where the difference is much smaller. All right, so the color of light, just as an aside, corresponds to energy, right? So the closer you are to the red end of the spectrum, the lower the energy. The closer you are to the blue end of the spectrum, the higher the energy associated with it.